morning. So, can I ask how many of you are familiar with GPFS? Thank you. And how many of you are familiar with RAID arrays and use them? Thank you. That gives me an understanding. Everybody, yep. Just want to make sure. Yeah. My name is Veera. I'm from IBM Almaden Research Center in San Jose. And I'm going to talk to you today about a feature that we recently added to IBM GPFS. It's a parallel file system that we use, that's used in several HPC systems. And we built this native RAID layer for working on 100,000 kind of disk, hundreds and thousands of disks, Petascale system. And obviously, we are talking about hard disks here. We still can't, even supercomputers can't afford hundreds and thousands of solid-state disks. And given that these are hard disks, so let's look at hard disk technology, what's happening. And yeah, the disk drives are bigger than they used to be 10 years ago. Yes, they are faster than they used to be 10 years ago. But they're not growing at the same rate at which they were growing 10 years ago. In other words, the curves are flatter than they were 10 years ago. So what this means is that to get the same performance rate of increase that we were 10 years ago, we need to use more of these devices, more of these hard disks, more components. So even though the curves have become flatter, all those inflection points that you see here in the wrong direction, be that as it may, all the government programs that are using supercomputers, they're not saying that, yeah, we can't increase, they still want the system performance to continue to increase at the same rate that matches with their algorithms and all the processing they want to do. So what this means is there are too many moving parts in the system, given that these densities are not increasing at the same rate. So here is a chart that shows, compares two systems, an ASCII purple system, a supercomputer that was in Lawrence Livermore, with a targeted system sometime next year. So if you really see, the number of parts are about 10 to 20 times or 40 times what it was in the past. So even though these number of components are increased, these disk drives have evolved, but still what's happening is their reliability has not caught up. So there are more number of parts, but their reliability has not increased. So what that means is the system that is using these components have to deal with the problems that are there. So the question is, with these parts, with these many moving parts, how do you build a system, a supercomputer, at an acceptable performance and an acceptable cost? That's the challenge we had when we started working on this project. So with that said, that's the problem. And here is the outline of my talk. I'm going to give you a quick overview of GPFS, parallel computing, RAID, and then move on to the challenges with traditional way of building things, using traditional RAID and traditional disk drives. And some of you probably will relate to the problems that I'm going to share with you. And I'm going to talk about the solutions we added, how we address these problems in GPFS native RAID. So GPFS originated at IBM Almaden Research Center, and even though it has moved on to become a product, IBM research has continued to be involved in delivering new features into the product. And GPFS, as I said, is used in a wide variety of supercomputer applications, aerospace, weather modeling, defense, national labs. A lot of places use GPFS. And it is also used in scalable NAS environments, but this talk is mainly focused on supercomputers. So a professor, Ken Batcher from Kent University, he humorously mentioned that a supercomputer is a device for turning compute-bound problems into I/O-bound problems. Now, what this says basically is that storage, even though it's a small part in a big supercomputer, which is primarily designed for computing, it should not be a bottleneck for supercomputers. That's the takeaway. So there are two models I've shown in the bottom here. One is a workflow model where the supercomputers do a bunch of computations with the data they've read, and then they write out the disks because the workflow is changing. They execute a barrier where all the nodes in the cluster write out to the disk, and then when they move on to the next phase of the operations, they read whatever they need to read for the next phase and move on to do the computations. That is one model. And the second model is below that, where it's a checkpointing kind of a model, where it's a continuous stream of computations going on, but once in a while, the supercomputer needs to checkpoint its memory to the disks so that it can do crash recovery. Now, if you see in these, what the point of these two pictures is to show that whenever there is I/O happening, computation is not happening. All those processors, all those compute nodes that are primarily there for computation, they're not being used, which means that's where it relates to the first code. It's half humorous, but the point is we don't want storage to be the bottleneck. And in other words, anytime the view of the supercomputer folks is that any time doing I/O is time wasted from computing. So how do supercomputers access these disks? They use parallel file systems. There are a couple of them, and GPFS is one such. And why do they use these parallel file systems? Because they give a single system image. There is so much storage out there, and you get a single system image. And they provide POSIX semantics, which makes it easier for programming. And also, these parallel file systems gives high throughput and load balancing. And so how do they do that, which is what we'll see in the next slide. So what GPFS does is that, so let's take an example of, so GPFS stripes both data and metadata on all disks, across several disks, across many disks. And let's take an example of, I'm sorry, I'm having trouble with this thing, so I'm going to use this thing. So let's take an example of a large file in one compute node. Now what happens is, if that file is, I'm going to go back and make sure these are clear. So on the top is the compute nodes, and the bottom are the I/O nodes, which are talking to the disks. Now the ratio here is an illustrative purpose. In reality, there are the ratio is very high between compute nodes to I/O nodes. They're connected over a high-speed fabric. And let's take a file that's in one compute node, and it's writing out this large file. What GPFS does is it takes that file and it stripes it across all the disks in the array. It's an animation. I have trouble with animations all the time. So this is a second example of a single file, but are being operated by all the nodes in the cluster. They are operating in different parts of the cluster, of the file. Or it could be that those green blobs are independent different files. In either case, what GPFS does is it again stripes it across all the disks. So the takeaway of this is it achieves this high throughput by striping across all the disks it has. That's the takeaway from this. That's what I want you to remember. So in reality, these disk drives are logical arrays, but then they use RAID, disk arrays. Right? What GPFS is thinking of a disk is actually a RAID array. So moving on to the RAID arrays, I'm sure most of you are familiar with this, but just to make sure we are all on the same page. So you start off with a bunch of disks, which is used for data and parity, and then you assign some spare disks, so that when a disk fails, the RAID controller can start rebuilding onto the spare space. And if while during that rebuild, if a second disk fails, starts rebuilding into the second spare disk. So there are two types of rebuild. One is a degraded rebuild, other is a critical rebuild. So the reason why it is critical The second type of rebuild is critical is because another failure, the RAID array cannot tolerate another failure. The array is in a critical state. And in the above case, it's degraded. It can tolerate one more disk failure, but it is still degraded. Why is it degraded? It's because its performance is degraded in both cases. The reason is, while the client is continuing to read and write, these are the RAID array is going to do a rebuild in the background. And if you can pay attention to these arrows, this arrow is a thicker arrow compared to this one. That's because the bandwidth to do the rebuild operation is twice as much during critical, because you're writing to two spare disks compared to one spare disk. But the point to remember is, this is a background activity, and RAID controllers typically give you some knobs to control the rate of this background activity. But then I'm sure as administrators, when the array is in a critical state, when it can't tolerate any more disk failures, administrators would like the RAID controller to rebuild everything as fast as possible so that the data is protected before the next failure. And RAID not only handles disk failures, but also handles media failures, media errors on individual disk drives. Again, it reconstructs and overwrites the data. And similar to the file system, RAID also stripes its data across all the disks in the array. So here is the overview of the simplified storage stack that I just showed you. One is on the top is the application, and then there is the file system. Underneath this is the RAID, and then the physical disks. Right? So depending on what the budget of the project is, you're going to either have SATA disks, SAS disks, maybe a mix of SSDs, but it all depends on the budget. The performance of the disks are determined by our budget. But the fact is, performance is important at every layer. The RAID has to perform, the file system has to perform in order for the application to see the performance effect. So any slowdown anywhere will show up in the file system performance. So what is the building block that's used typically to build these supercomputers? Right? So here is the building block. So you take, for a set of compute nodes, as I said, the ratio is high. Here it is a very low ratio, just for the sake of illustration. For a set of compute nodes, there are a set of I/O nodes, a small set of I/O nodes, and each attached to a RAID controller, twin-tailed. And each of the RAID controller talks to a bunch of disks, possibly multipath. Now, Now what happens if this is the building block? How do you build a cluster using this building block? Is you take this one building block and then you replicate several of these building blocks, connect all of them together in a network. Now you have a huge system. That's how you get to hundreds and thousands of disks. But the problem is, if, let us say, in a big population of disks, there are going to be failures very, very often, because it's a lot of disks are there. Now statistics comes into play. Now if there is one array that is rebuilding, you would think that the performance of only that array is affected, so what's a big deal? But that's not the case. The entire file system performance is affected even if one array is rebuilding. The slowest component affects the overall system. That's because these are not real, they are not workers. They're not, these arrays are not workers that can be anonymized. They basically have some data. If that array holds the data, you cannot go to another array and get the data. You need to go to that array to get the data. Right? So that's why the performance is a bottleneck. If these are any random place, if it's all write operations, you could do some workarounds in the file system to avoid that slow array and go to elsewhere, if that's only possible for a write. And even then, you're going to have one array's less of performance. And for how long are you going to do that? And you've got to, at some point, come back to that slow array and access it for the capacity it offers. So what we decided to do was, so this is the highlight of the first problem that I told you is the rebuild problem. With hundreds and thousands of disks, even if you assume an MTBF of 1,000,000 hours for a disk drive, you're going to see a failure. One disk is going to fail every 10 hours in this 100,000 disks system, right? So which means rebuild is happening on a daily basis on this 10,000 disk system. And if rebuild is going to be happening every day, if one array is going to always rebuilding somewhere in the system, the performance of the entire file system is affected all the time. So this is one problem with the traditional RAID. And some of you might have experienced this too. And of course, this is what is spoken a lot in the industry, that disks are getting bigger and bigger and they're taking longer to rebuild. And a couple of years ago, there was this question even raised, is RAID dead? And some folks saying, no, RAID is really not dead. And the problem that they are saying is, this is the problem. This rebuild problem is what they're talking about. Now, is that the only problem? Not really. Now, when there are so many disk drives, the first order problem is these disk failures. But then there are these second order and third order kind of problems start to show up, which is basically, you start seeing corruption issues from the disk, right? And that is another issue, and I'll go into the details of these a little bit later. But there are two issues in the traditional RAID controller. What I'm trying to say about the silent data corruption is that disks tell you that here is the data that you wrote, but it is not exactly what you wrote, right? That's what I mean by corruption, and I'll show you some more information on that. So to address these problems, what we decided to do is we said we're going to change this picture where we're not using any external RAID controllers. Instead, we implement a native RAID layer inside the file system. So that directly does the RAID. Now, the main reason why we were trying to look at this kind of a option was that it was motivated by cost. But then it turned out that there were these other problems that I told you about. The rebuild problem could also be effectively addressed here, and also the data integrity problem can be addressed really well at this layer of the file system. So the stack looks from this to this because of the native RAID is integrated into the file system. And the problems it solves are it addresses the slow rebuild performance. And the way we address it is we use the declustered RAID. And I'll talk to you more about what is declustered RAID. It is already implemented by some other products. Even IBM, the IBM XIV also implements it. And at a network RAID layer, but this is at the disk block RAID layer. And we also solve the problem of data integrity on disk drives by using end-to-end checksums and version numbers. So now going to the first solution of these high-performance rebuild. So here is this is again an animation chart. I hope it comes out right. So what we are showing, this is for illustrative purpose, so that you can get the idea of declustered RAID. So each one colored pair is a RAID 1 array, mirrored array. So you have 3 such arrays and 1 spare disk dedicated. So this animation is trying to show how you take this traditional 3 arrays, each of which is a RAID 1 array, and decluster them, right? So you take the first array and you spread it across the 7 disks. So on both the bottom left and right, you have 7 disks. So we're not taking up any more capacity, except what we're doing is declustering. We're taking those the strips. I forgot to tell you that. So I told you that RAID also stripes, and the column is an entire disk, and the rows are stripes, the RAID stripes. So if it was a white, so this one will be the first blue copy will be the primary copy, and the second is the mirrored copy, right? And then so we take those 2 stripes and stripe it across all the 7 disks of the declustered array. So that's what we do with the first one, and we do the same thing for the other 2. Right? Now we start to decluster the spare space also. The yellow is the spare. And with this, what you have is a declustered RAID array. Right? So this shows an example of the rebuild problem, just to show you, illustrate again. So take, for example, this disk is failed. What happens in the traditional rebuild? You read from the mirror and write it to the spare disk. That way, so that the RAID is no longer having faults, it is fully replicated. It can tolerate one more failure. So that's what is the rebuild operation of a mirrored RAID looks like. Now what happens if a disk fails in a declustered array is consider the same disk that has failed, the fifth disk in the declustered array has failed. Now what happens is you start, whatever data was not there, was lost because of that disk failure, is now replicated using the mirrored copy that is stored on all the other disks in the declustered array. Now if you take this example, going back to this, look at the performance. So we are reading from this one disk and writing to this one disk. That's the throughput used. Now whereas in the case of declustered array, the graph shows that all the disks in the array are not only read, are also written. Right? So this is where what we get is, what declustered rebuild gives is two things. It gives you, if you want to rebuild fast, you can do that because you have all the throughput. Or if you want to provide less disruption to the user, you can do that too. So it gives you two options. And now this is an example of a RAID 6, again an illustrative purpose using 4 disks because my screen doesn't fit the width of the real array. So you take on the left side, you saw what I show is traditional arrays. Each color is a RAID 6 array by itself. And on the right side is a declustered. This is how it will look if you're declustered. Now what happens if 2 disks fail in both cases? Now the table below tries to show the difference actually. Now here what happens is when 2 disks fail in the green array, the green array suffers 2 faults in every stripe of that array. Whereas in this case, only the red array suffers 2 faults. All the other arrays have suffered only 1 fault. This is an interesting side effect of declustered array. Actually, this is the main reason for doing this declustering. It's not only throughput, also the fact that when 2 disks fail, not all the data, not all the affected stripes have 2 faults in them. So what this means is there's only about, in this example, in a RAID 6 example, about 10% of the data is only critical, right? Whereas in 2 fault happens, all the stripes, all the 7 stripes in this example have 2 faults, whereas here there's only 1 stripe that has 2 fault. Now the effect is very similar, actually better when it is a 3 fault tolerant array. About only 1% of the data is affected, it becomes critical, whereas the rest of it is not critical. So what this means is I can quickly rebuild only the stripes that have 2 faults, and the rest of the stripes with 1 fault, I can take my own sweet time to rebuild. So that way, during this stripe rebuilding, the small percentage of stripes that are critical when I'm rebuilding, those alone, at that time alone, my application workload will see a performance degradation, severe performance degradation, because I want to rebuild as fast as possible. Whereas during the rest of the time, when I'm rebuilding the single faults, I can kick back and relax because I can tolerate more failures. So that is the main advantage of declustered array. Now, this is a Power 775 disk enclosure this is the main motivation we did this. And this is the disk enclosure that goes with the Power 775 processor rack of IBM. And what this disk enclosure, the number of disk drives this disk enclosure can hold is 384 disks. And I don't know about you, but that's a hell of a lot of disk drives, in my view. And what you see in the middle is the blowers. So it can have disk drives in the front and in the back. And the disk drives are mounted on a carrier. So there are 4 disks in each carrier. And compared to other models where you pull the entire disk drawer out to service a failed disk, where you move all the disk drawers together, and disk drives don't like that, moving it while they are running. Or you attach a carrier through a cable, right? Cables also don't like movement very well. So this one doesn't do either. If you have to service a disk drive, we power off all the disk drives, and we indicate there are some LEDs for each of the disk drive. There is an LED that indicates which disk needs replacement. And before replacement, we power off all the disk drives. The service person pulls the carrier out, looks which disk needs replacement because there's a light there, replaces that, puts it back in. We power up all the disk drives, and we go from there. And we keep track of. The question would be, if you told me this model, I would be very, very worried about. Oh, you're going to take, in order to replace one disk drive, you're going to take 4 disk drives offline, and are you going to rebuild all those 4 disk drives? Not really. So we keep track of. Let's say the first disk drive is bad. Anyway, that's bad. We have rebuilt it a long time ago onto spare space. All the rest of the 3 drives have data in them. Now, if a read is coming during this time, we can reconstruct and give the user the data. If a write is happening, we have to keep track of what are those writes that we didn't write to this location. And then when the carrier is inserted back again in a few minutes, we go back and write it to the home location. So we don't do an entire rebuild operation, but just a selective rebuild of those data that was not written when the carrier was in service. So this is a photograph of a prototype of a machine in our lab. So just to give you the scale, the disk drive, the enclosure goes all the way to the back of the picture. Yes. That's right. So this picture again shows the disk drives in the front and in the back. Think of it as a top view of the enclosure. So each of this column is a carrier. It has 4 disks. And we dedicate a few of them for SSD, for metadata, that offers higher performance for metadata operations. And we take all the disks in one row, one disk from each carrier, and make a declustered array out of it. So it's a 47-disk declustered array. So with a 47-disk declustered array, we don't do just RAID 6. We do one fault tolerant more. We tolerate three faults by using it's a 11 wide stripe with 8 data blocks and 3 parity blocks, 8 data strips and 3 parity strips in a 1 RAID stripe. And we also support 4-way replication. And as I said, it is distributed across 47-disk array. Now what this means is, if one disk dies, which is the most common case, if one disk dies in an array, we will rebuild very slowly. This is counterintuitive from what you may be used to. You set the rebuild at 1 speed, and all types of rebuild run at that same speed. That's what RAID controllers typically do. But here, we give you 2 knobs, one for what we call the normal rebuild, which is the normal case, where one disk dies. Disks are going to die every day, so we call it a normal rebuild. It's no longer an error scenario, because it's in a population of 100,000 disks. Disks are going to die every day, and the system is going to rebuild, and it's a normal rebuild, because the performance of the client workload is not affected. It's affected by 5% maybe, but not by 30%. And when it is three disks die in the same array, not in the entire population of 100,000 disks, we're not talking about that, but we're talking about 3 disks in a population of 48 disks, which is a very, very rare event. In that case, 1% of that 48 disk data will have 3 faults, and during that 1% rebuild, which is going to take in the order of minutes, not in the order of hours, not in the order of days, we quickly rebuild that by the client workload will be affected because it's a critical at that point. We don't want to tolerate, we cannot tolerate one more disk failure. So we'll rebuild at a very high rate, but that's just 1%. And that high critical rebuild will last for 5 minutes maybe, 5-10 minutes at the most, in the order of minutes, and you're out of rebuild. And you as a system administrator might get a call, somebody would notice it in 5 minutes and tell you that, hey, my system is slowed down considerably, and you log in and you will check what's going on. By the time you do it, the system would be out of critical rebuild. And you will say, well, it's all fine now. So that's the idea. So we not only support 3 fault tolerant, we also support RAID 6 and a three-way replication. So bottom line is we use the native RAID layer in GPFS uses declustered RAID to address the problems in the traditional rebuild, the traditional RAID arrays. So moving on to the next solution that we added, which is this data integrity solution. So, so imagine you're the user and you have a disk that has a data block A, and you try to read this data A from the disk, and if the disk returns you the content A, then everything is good. But if the disk gives you B, then we call it a corruption, right? So in those cases, that's when the disk drive thinks actually the content is B, but actually what you wrote is A. Now why it gives, there could be lots of factors, but bottom line from our perspective, it's better not to give me data, instead of giving me bad data, right? And just to remind you that all the widely publicized 5 nines number, how reliable the system is, how available the system is, does not consider data integrity issues. The assumption there is the data, it's 100%, data integrity is 100%. That's the assumption there. So that number, that figure, the 5 nines figure doesn't include data integrity problems. Now, these undetected disk errors are known in the literature by a variety of names. Some call it silent errors, some call it phantom errors, etc. But they are not the same as media errors. Media error, the disk tells you, I cannot give you the data. That's great. It's not great, it's bad that it's not giving you the data, but at least it tells you, it's honest about it. Whereas in the other case, not that it's dishonest about it, it just doesn't know, it's not aware that it is bad data. And there are papers in the literature that talk about experiences in the field where disks have these corruption issues. And some of us at Almaden Research Lab took those data. So the problem is because this is silent, you don't have a rate how often this happens. There are no statistics on this corruption issue because it's silent. Suddenly one day some crash happens and maybe you reboot the system, or you think the operating, the blame goes on all layers because you don't know what caused the problem. So there are not much statistics. But so we took some data that was published and we abstracted the I/O, and we basically modeled, and we estimated that about, even in a 1,000 disk system, will experience a data corruption once every 5 years. Now, that's an estimate, but you can imagine what is the number if it is a 100,000 disk system. So we just cannot afford to ignore this problem. That's the bottom line. And what are the types of errors? Why do we see this corruption? There are a variety of factors. Disk drives are complex. They're not as simple as we would like to think they are. In school, in textbooks, we read that tracks are circular, which is true if you look at it, if I look at it. But if I am the disk drive head, I'm looking at the track, it's actually a very curvy, windy track that I'm following. And it's very possible that I have, with good all intentions, I'm trying to go to one track, but I land in a different track due to vibration issues, due to thermal issues, So many issues are there in a disk drive. And not only in a disk drive, even there are so many other layers above it. Corruption could happen anywhere. The system above it needs to be able to deal with it. So when it comes to disk drives itself, what are the various problems in which a write can go bad? Basically, the disk drive, when it writes, it doesn't do any checking of did I write the data correctly. Only when the time of reading, it goes back to figure out, and if it can find a problem, it will tell you there's a problem. But while writing, due to, let's say, a head issue or hardware issue or a firmware issue, the data, instead of landing in one location, could land in yet another location. We call it a far off-track write, in which a different block is totally corrupted. That's one type of corruption. The second corruption is the data is very close to the existing track. The disk really meant to go to that track. It went there. It was writing it, but there was some vibration. The data landed very close to it. It's a near off-track write, we call that. And then there is the third case where the disk totally doesn't write to the disk because the head is too high, or due to some firmware issue, hardware issue, God knows what, it doesn't write at all. And then when it comes time to reading, that's when you will see the effects. And then even if the data was properly stored on the right track, right location, there could be problems while reading. Right? So that is a separate class of read errors. And these problems can be either transient in nature because of some vibration happening, or could be it's a persistent problem because of a hardware problem, let's say. So typically, how do systems address this? They attach a checksum trailer to the data, and they write the checksum and the data together, so that when reading back, I can make sure the data read matches the checksum that I stored with it, so that I can detect any corruption. This will detect corruption in the sense of it will detect if it is a far off-track write. Instead of writing to this track, I went far away and wrote to a different track. Now when I read it, that location, I'm going to get a totally different problem. So I checksum maybe, then I can detect it. But this method does not detect dropped writes. If I totally forgot to write, if the disk drive forgot to write the data to the location, then what will happen is the next time you go to read, you will get the old data, stale data. And the stale data will match the checksum that is there in it. And you might think that, hey, the data and the checksum match, must be right. Not really. It's old data. So what that means is we need a way to validate the checksum trailer itself. The checksum validates the data, but then who's going to validate the checksum itself? We need a validation, which means that validation has to be not stored with the same data again, because that's susceptible to dropped writes. It has to be stored at another location, at a different disk drive or a different mechanism. It can't be co-located, in other words. The checksum and the validation of the checksum cannot be co-located. It has to be located separately. So that's what we do. So we use version numbers and checksums. We store the version number in the metadata and we log it so that there's no performance penalty for it. And what we do is at the time of reading, we read the data, make sure the checksum matches, but before even doing that checksum verification, we make sure the checksum block is valid using this validation information. And we do this end to end. What I mean by that is, so in a write operation comes from the compute node to the I/O node. That is checksum. It's a network checksum. We don't rely on the TCP checksum. We also add on top of that our own checksum layer, and we verify that the data between the transaction between the two nodes is correct. And then when we go to the write to the disk, we write the validation information and write the validation to the metadata. Same way while reading, we read the checksum block, validate it, and then again use checksums to send it to the client node, the compute nodes. It's an end-to-end solution. So what do we store in the trailer is not just checksum alone. It's not a blind checksum. It's a very fully aware trailer that tells you who I am. I am a block in this stripe of that strip, of this array, so that even if you take this data due to some corruption and wrote it to a different array totally, we can detect that this data doesn't belong here, even though it looks consistent from other aspects. If the block doesn't say it belongs to this array, then that block is corrupt. So we store quite a lot of information in the trailer to make sure we catch this. Again, this is all from experience that we don't want to deal with these problems again. So we are a RAID controller. So we have to do, other than those two problem solving, we have to do other things that the typical RAID controller does. We are the RAID layer now. So as I said, when a disk is temporarily out of service because somebody took the carrier for servicing, or if the disk was misbehaving and we were diagnosing that disk and we couldn't do write operations during that diagnosis, those things we selectively rebuild using a background operation. And when a disk fails, we restore the redundancy. And we do this by, instead of traditional rebuild, there's only one type of rebuild, as I told you, because there is this case of some stripes having 3 faults, some stripes having 2 faults, some stripe having 1 fault doesn't exist in a traditional rebuild, traditional RAID. Whereas in declustered RAID, in the case of 3 fault tolerant declustered RAID, only 1% has 3 fault. So we quickly rebuild that at a critical high rate, and then we switch back to a low rate and rebuild the 2 faults and then the single faults. That's what the background rebuild does. And then we also have a rebalance task. When you insert a disk died and then you took a new disk, replaced it, now the disk has full of spare capacity, right? And we want to distribute that spare space across the array so that when it comes to again using that spare space, we can use a throughput on all disks. So we call that operation as a rebalance operation. And when I don't have to do either a rebuild or a rebalance, everything is hunky-dory, then I'm going to make sure the data on the disk is fine by doing a background scrub operation where we read the data, the parity, make sure the checksums are right, we make sure they're consistent with the data and parity, and then fix any problems we find. And then we do it opportunistically, these background tasks. We don't take up the client work, we don't impact the client workload unless it is critical operation. If it is a critical rebuild, we presume you want us to rebuild as fast as possible. And other than that, it's all a background operation. And so we also have a disk hospital layer where we diagnose and treat disks, if you would like to think of it that way. So when a disk reports an error, we have to figure out what is the problem. Is it a path problem? Is it a media error? Or is it a total disk failure? Right? We have to diagnose those 3. And then after we have decided what really happened, we have to take corrective actions. If it is a media error, fix it. If it is if it is a disk is totally unresponsive, then we even power cycle it through. We go through the control path of the disk enclosure. We power cycle the disk to see if it can be revived. And if we determine that the disk is really dead because the disk itself says so, or it is totally not there, then we have to take corrective actions such as rebuild. But after some point, we keep maintaining health records of these disks on a per disk level, per disk basis. And if the disks have been either affecting performance or reliability, then we have to take it offline. There's no point in having this disk. And we take it offline, and that's when we schedule replacement requests. That's when service person will come, and that's at the service time. We need to power off the disk drives, as I said before, to allow the person to pull the carrier out, and we show which disk have to be replaced by lighting the appropriate disks in the carrier, and all that stuff that goes with the disk replacement. So to summarize, what I told you was this: when there are these hundreds and thousands of disks, the traditional RAID has this slow rebuild problem and has this data integrity issues. We address both of those problems, one by using declustered RAID, and second by using version numbers and end-to-end checksums for the data integrity problem. And We also offer cost advantage because there is no rate controller associated. This function is now done in the I/O node. And how is it possible? It's because these days these I/O nodes come with extra processing power. There are additional cores anyway. And so the function can be absorbed into the I/O node. And typically when these talks, I'm from research, and whenever we give such talks, it's at a prototype stage, and we'll have to kind of say when it will be available in the near future in some time. But fortunately, I'm glad to say that we just shipped it last month, and it is already installed in customer locations. And like GPFS, it supports a wide range of applications and systems. So that is about the GPFS native RAID. Thank you very much. If you have any questions, happy to take them. Thank you. I guess my talk was very easy to understand. Okay, thank you very much.